Hello everybody, you welcome to my signal processing and analysis course. Here is the part dealing with digital filters. You're welcome. Here is the detailed content of this part. We start with definition of linear discrete time invariant systems. Then we deal with infinite and finite impulse response filters concept. For illustration, some applications of FIR and IIR filters will be proposed. The last part of this course will be devoted to digital filter synthesis based on their spectral response. Here are some interesting definitions. A discrete system associates for each series of inputs x a series of discrete outputs y. A linear system associates for each linear combination of inputs a linear combination of its outputs. Let's consider the direct distribution. A series of discrete values can be written as a sum of direct impulses ponderated by these values, given by the following expression. Let H be the response of a linear discrete time invariant system to the series of direct impulses. Then we get the output expressed by means of the response terms as follows. The first equation is due to linearity, and the second equation is due to time invariance property of the system. The output signal is then a convolution of the input signal with the direct impulse response. Thus, in that way, the impulse response completely characterizes the response of any such filter. What is the stability condition? A linear discrete time invariant system is stable if for each input bounded series corresponds a series of bounded outputs. A necessary and sufficient condition for a system to be stable is the sum of absolute values of its impulse response is bounded. Here is a demonstration of necessity of the stability condition. Let's consider the series values of x given by the sign of the impulse response h. Then applying the convolution product relation expressing the output we get. The first output sample can be expressed as the sum of all the absolute values of the impulse response h. According to this relation, if this sum is bounded, stability condition is not satisfied, so it is necessary to get it. Here is a demonstration of satisfaction fact of the stability condition. Let's consider the series of bounded values x. We then get for each integer n, it exists a scalar m verifying x of n, which is strictly inferior to m. Then the nth output is inferior to the same scalar m multiplied by the sum of absolute values of the impulse response h. If we have the condition that this sum is bounded, this output is then bounded. Here we explain the concept of proper functions in linear time invariant systems. If we apply at the input of a linear time invariant system of impulse response h a digital signal of a frequency f given by the following complex number, the product frequency by sampling period Te is called the reduced frequency. The corresponding output is given by the following equation that can be written as the product of the Fourier transform of the impulse response and the input x. This relation is very important. If we can decompose a signal into proper functions, the output has as a spectre the spectre of the input signal modulated by the spectre of the system impulse response. A linear time invariant system can denote an infinite impulse response filter or a finite impulse response filter. A finite impulse response filter, denoted by FIR filter, is a filter whose impulse response or response to any finite length input is of finite duration because it settles to zero in finite time. So, for this kind of filter, the output can be expressed as a linear combination of input sequences as follows. The infinite impulse response filter, denoted by IIR, when such a system is subject to an impulse or any signal of finite duration, it responds with an output waveform that lasts past the duration of the input, eventually decaying exponentially in one or another manner. They have internal feedback and may continue to respond indefinitely, usually decaying. The output can thus be expressed by means of inputs and previous output samples, as follows. Infinite impulse response and finite impulse response filters are illustrated here in both figures. Here is a study of infinite impulse response filter. IIR filter model many natural systems. They are defined by the above equations. The output is related to previous values of output as well as inputs. The Z transform of this equation is given by this relation. And we thus get the expression of the output Z transform versus the Z transform of the input, leading of course to the following transfer function. This transfer function can be written as a ratio of input polynomial to an output polynomial. From the transform function, a representation of poles and zeros can be useful. Zi is the coordinate of points zeros and Pg are the coordinates of points poles. Indeed, it is possible to get the spectral response of the system by replacing Z by exponent of G to P if the reduced frequency. M of the coordinate Z is thus situated on the unity circle. The transfer function H can be expressed as a ratio of distances product as follows. The waveform has a general aspect of the illustrated in the curve in the figure below. For more understanding, we consider here an example. Let's consider the IIR filter described by the following difference equation. The impulse response can be computed accordingly, and we can get as output value the following. The filter is unstable if and only if the sum of b integer exponents is bounded, which condition is equivalent to the absolute value of b, which is less than 1. In that case, its transfer function is given by this expression, with one pole equal to b. The module of the transfer function versus frequency is illustrated in the above figure. Now, the finite impulse response filter is described by the input-output discrete following relation, where the output is expressed only with input samples as follows. An example of such filters is illustrated here in the decimation filter or downsampling example. Let's consider the filter given by the following difference equation. We thus get the Z transfer function of the filter given by the below equation. The frequency behavior of the filter can be studied by replacing Z by exponent G to P and multiplied by the reduced frequency. We thus get a cosine function with a linear phase. The magnitude of this transfer function is illustrated in the above figure. In the preceding slides, we have shown how linear time invariant filters spectral response can be obtained by considering the discrete input-output difference equation. Now we are interested by the reverse operation, that is, consisting on generating the discrete input-output equation, yielding a practical implementation of the filter, given a spectral response of the filter. We suppose in the synthesis that the filter phase is linear with respect to frequency. From the spectral response of the filter, the different samples can be considered as points of the frequency transfer of the impulse response of the filter. Thus, the synthesis of the filter is rather a computation of the impulse response by the inverse Fourier transform of H given by the following equation. Once we get the impulse response of the filter, the input-output relation is well defined. As a conclusion, we have dealt in this part of my course with linear discrete time invariant systems. We give their definition and their analytical description by means of difference equation. Then we have given definition of FIR filters and IIR filters and the discrete difference input-output relation allowing their implementation. Then we have presented a study of spectral response of IIR filters given their difference equation. An illustration example was considered. Then the spectral response of FIR filter is given, their difference equation is established. An illustration of example were considered a decimation filter and a recursive filter. In the last part, we have proposed a synthesis method of digital filters given the spectral response. For further information or question, please feel free to contact me by the email above address.